Greetings, comrades. This clip is pitched to Year 8 students. It is mainly going to cover light waves. There will be some sound waves in part 2 of this test revision summary. Now, given we covered both sound and light waves, we need to be specific in terms of how we describe the manner in which they travel. So as light waves travel forwards, they're moving as transverse waves with magnetic fields pulling them sideways and electrical fields pulling them in an up and down fashion. So some key properties of those light waves that we can plot is we measure them in terms of their frequency. So if we look over here, we count the number of wavelengths per second, and we measure that in our units, hertz. Also, something to be mindful of is when we're describing the amplitude of a wave, we're doing that in a vertical manner from the midpoint, the origin of the wave, up to the crest. Frequency I've already talked about. The crest is at the top of the wave and the trough is at the bottom of the wave. Now, unlike sound, which needs a medium to transfer their kinetic energy through the vibration of particles, light can in fact travel through a vacuum, through space, via electromagnetic radiation using those minute light particles known as photons at a rate of 300,000 k's per second. So light can be transmitted through a vacuum, through a gas, through a liquid, and through a solid. But given light travels in transverse waves, the greater the density of that medium in terms of the energy that is moving in right angles from the direction that the light is traveled, the greater the resistance and the more that it slows down the frequency of those light waves. So key point, the denser the medium, regardless of whether it's a solid, liquid or a gas, the more the frequency of those light waves will slow down. There'll be less wavelengths per second. What do we mean by the electromagnetic spectrum? Well, electromagnetic energy is the way that light travels. A spectrum is simply positioning all the forms of light on a continuum based on their frequency. So we have a low end, we have a high end in terms of the number of wavelengths per second. In terms of the visible part of the spectrum, we're talking about humans here, and the very small part of the electromagnetic spectrum that humans can see based on the functionality of their cones in their retina, which I'll get to a bit later. So again, there's a whole bunch of other forms of light in the universe that we simply can't see because the photoreceptors in our eye just can't detect it, which is actually a good thing, because if we could basically process all light, everything would be a fuzzy blur. Now, I don't expect students to memorize the numbers here, but just be mindful that when we look at the numerical aspects of the visual component of the electromagnetic spectrum, our units are nanometers, 1/1,000,000 of a millimeter. And at the lower end of the visual portion of the electromagnetic spectrum, think about your rainbow again, we have our violets and blues, and then the mid part, these green and yellow waves have more energy, a higher frequency. And then at the upper end, this is the limit in terms of the, the level of frequency that the cones in our retina can actually process in terms of around that 750 nanometers. Now, be mindful of the dichotomy of a few of the concepts that we cover in this topic. And by dichotomy, I'm talking about opposites. Remember last year when you were year 7s and you did a dichotomous key, similar kind of process here. So when we talk about luminous objects, these can generate their own light, and it's actually hard to think of many examples of this apart from the sun, fire, glowworms, stars, etc. And then we have illuminated objects which cannot generate their own light. They only can merely reflect it, e.g. the moon, a mirror, water, depending on how smooth the surface is, and we'll get to different types of reflection a bit later. Now, when light traveling in transverse waves hits a medium, one of three things will happen. Either that light will be transmitted through and the photons will basically come out the other side of that medium, or the light will literally bounce off, photons will bounce off that medium, and again we'll get into some angles a bit later. Or the third option is the light will be absorbed and that energy will be transferred in terms of heating up that medium. Okay, some more dichotomy. Regular, aka specular, versus diffuse reflection. So with specular or regular reflection, that will be off a smooth, even surface, and we will get a sharp, clear image. If we have a rough surface with all these little contours and ridges, which we might have on a bumpy lake or water body, then because all of that, the light basically reflects off in different directions, we get a blurry, unclear image. Now, when the light hits the medium, one of three things will happen. If the photons totally transmit through that medium, then we call that a transparent medium. If only some of the photons penetrate through, and so therefore we lose some of our light, which is what we have with frosty glass, we call that a translucent medium. If none of the photons come through and we can't see anything, like if we shine a torch on a chunk of wood or a brick wall, we call that opaque. And that's how we generate a dark shadow. A light shines on that opaque image and then a shadow is cast behind it. Okay, let's go a bit further with specular, aka regular reflection. So we've got a hard, even surface here, our mirror. And we start with an imaginary line called the normal line, which we draw perpendicular to that mirror, 90 degrees, creating a 90-degree angle on both sides. And we shine a ray of light onto that mirror. We call that, coming from the source, the incidence ray. Then what will happen is some photons will bounce off that mirror, and we call this the reflected ray. Now, if we get our imaginary protractors out and we measure the angle between the source of the light, the incidence ray, and the normal, we will have the same angle if we measure it between the normal and the reflected ray. And that covers the law of reflection. The angle of incidence must equal the angle of reflection. Now, be careful if you get a question like this. So we're told that the angle here is 56 degrees and our mission is to work out the angle of incidence, the angle of reflection, and Q here. So given we know that the angle between the normal and the mirror is 90 degrees and we've got our 56 here, we can simply just work out our angle of incidence by subtracting that 56-degree measurement from 90 and we get 34 here. Now, given the law of reflection says that the angle of incidence equals the angle of reflection, this one must be 34 as well. And so therefore we can conclude that Q is also 56 degrees because this is also a right angle here. Sorry for the mess there. Now, be careful when you get a question on concave versus convex, because is the question asking about mirrors or lenses? Because potentially your answers will be a bit different. So a concave mirror curves inwards versus a convex curving outwards. In terms of light, the incident rays that hit in a parallel manner a concave mirror, this will cause them to converge back inwards. Converge means they merge together, and so where they meet is called F, our focal point. And when we have a concave mirror, the effect of that is to magnify the image, and the trade-off there is that will reduce how much we can see, our field of view. For instance, when we have a dentist putting in a concave mirror behind the back of one of our teeth to find a cavity. When we have the concave mirror, we'll get the opposite effect. So the reflected rays will diverge. Diverge means move away from each other. So therefore, if we want to find our focal point, we'll have to trace around the mirror and basically get a ruler out and draw these lines and find a focal point, which would be behind the mirror. And so therefore we use convex mirrors when we want to shrink the images. So that's what we might use for a security one in the corner of, say, Kmart. And the trade-off is that we actually increase our field of view, because if we're using that security mirror, we want to be able to see the whole store by just looking up in a corner. So lenses. So a convex lens, fat in the middle, thin on the ends, as opposed to the concave lens, thin in the middle, fat on the ends. So when we have incident rays that are being this time transmitted through a convex lens, that will cause those rays to converge inwards onto a focal point. And if we think about the lens in your eyes, hopefully that's at the back of the eye on the retina. So we have a sharp image. So therefore the opposite will occur with a convex lens. It'll cause the light rays to be transmitted through and they'll diverge away. So therefore, as we can see here with the convex lens, we will get our focal point behind the actual, in front of the actual convex lens, whereas we'll have to work backwards with a convex lens to find that focal point. So the cornea at the front of your eye and the lens right here, which is convex shaped, have a job to refract light inwards so that basically that light converges on our retina. And if the cornea and the lens are doing their job properly, then our focal point will be bang on our retina and we'll have a clear image. Now, if you're short-sighted, the focal point will be in front of the retina. So therefore, we're going to be short-sighted. So we'll be able to read our phones, our TikTok messages, etc. But we're going to have a bit of problems playing sports, seeing objects in the distance. If we're long-sighted, then the cornea and the lens are not adequately refracting the light inwards. So the focal point would be metaphorically behind the retina. And so therefore we're okay with our long-sightedness, but we can't read those TikTok messages we're getting on our phone. So to correct that, if we're far-sighted, we'll need a lens that is concave shaped to help with the necessary additional refraction required. So those light rays converge bang on our retina so that we get a clear image. If we're short-sighted, aka nearsighted, then we'll go with a concave lens. So therefore that will cause the divergence to a degree of those light rays. And so therefore, again, that will extend the focal point back so that, again, it's occurring in terms of those converged lines that are hitting the retina. And again, we get that sharp image.